Welcome to the office. I want to take a look at an example that is interesting, uh, eh, partly because it allows us to better discuss or better identify normal subgroups. And so what I want to do is I want to present this, but it's going to take a few details that are kind of stored away in our memory, or maybe various notations that we haven't used a whole lot in this course. So I want to try to remind us as I'm using those notations and these ideas. So the first thing that I want to do is I want to remind us about equivalence of sets or equivalence of orders. Two sets have the same order if, right, this sort of thing. So, or the same cardinality, right? So I want to say that the set A has the same cardinality as the set B if and only if there exists a bijection F from A to B. Okay, so I have these set sizes are the same if and only if there is a function that is one-to-one and onto from A to B, or from B to A, it's the same thing. Since it's one-to-one and onto, we have the inverse. All right, so I have this idea, but I can also use this in some other ways. This relationship is very, very strong. So if I have that the size of two sets A and B are the same, and F from A to B is onto, then, so if I have some function from A to B where A and B are the same size, then F is also 1 to 1. I get 1 to 1 for free. So if I know that the set sizes are the same and I can find a function that is onto from one to the other, then I know that that function is also 1 to 1. Similarly, if I have that the two sets are the same size and I have some function from A to B is 1 to 1, then I may conclude that F is onto. That is, it is a bijection. So I really like having these ideas in hand and ready to go. If these things are new to you, you're not familiar with them, not familiar, you should try to prove them. I believe that these are pretty standard for an introductory course on proof techniques. So hopefully it's something that you've seen before. Otherwise, you're welcome to simply use them for now without proving them, but the interested student should prove them. All right, so I want that idea in hand. And let's see here. I also want to use this other idea of an indexing set. So if I refer to I is an element of I is an indexing set. The nice thing about using I as an indexing set is that I don't have to know the cardinality of I. So sometimes you'll see I belongs to 0, 1, 2, all the way up to n, for example, integers from 1 to n. Or you might use something like I belongs to z, and that's fine, right? An infinite collection, but it's countable. Or you might even see, on rare cases, I being a real number. Technically, you could let it be a complex number, right? You have a lot of different options there. But the point is when I don't know what the index should look like, I can just use this general indexing set for I an element in here. And then I can talk about X sub I or A sub I or whatever I want to talk about, right? Those things that I want to index, a collection of elements, a collection of sets, a collection of functions, whatever they are. I can use I as my indexing set to refer to the various functions. All right, so I have this collection of ideas and notations in hand. Let's go ahead and approach this problem. Let G be a group containing at least one subgroup of a fixed finite order S. Okay, We want to show that the intersection of all subgroups of G of order S is a normal subgroup of G. Oof, okay. We got this. No problem. So I want to let S, this is going to be capital S, be the collection of all elements or all sets Si. So this is also a capital S, Si, where I is in I, some indexing set. How many sets of order S are there? I don't know. But what I'm saying is that the order of each of these things is lowercase s. So this is, let this be, let capital S be the set of sets, or the sets of subgroups that are of order S. All the subgroups of order S. That's just these things. Everything in here is all of the subgroups of order S. That's all that I want. There might be 5 of them. There might be many of them, right? I don't know. So let S be this. Okay, excellent. And I want to recall that the intersection of an arbitrary collection of groups is a group. Good. Right, that's good to know. I need to know that the intersection of all groups of order S is a normal subgroup. Okay, I'm first verifying mentally through recollection here that when I take that intersection, I do indeed get another group. What I want to do is I want to let H be that intersection. So I want to let H be the intersection for, now let's see here. The letter that I want to use is J. So I used I up here. I'm going to switch it over to J because we're also going to use inner automorphisms, and I don't want to mix up my I's and my J's there. So I'm going to move transition over to using J. So for J in the indexing set, I want to consider the intersection of all of the J's. There we are. The intersection of all of the groups, the subgroups of order S. All right. Again, that is the intersection of all groups, all subgroups of order lowercase s. That's what this thing is. All right, so good so far. I want to let G be an element of the group G and consider the inner automorphism given by I sub G, a function from G to G, a mapping defined by, right, this is not a new definition, I'm just using the same definition for inner automorphism. Defined by I sub G of X is G times X times G inverse. All right, so what I would like to do is, let's see here, I would like to eventually work towards that my left and my right cosets are the same is essentially where I'm trying to go, right? But in order to get there, I have to get this subset containment. I need to get that for each G, right? So that's the G that I'm interested in here. I want to show that this inner automorphism is going to fix this subgroup H, right? That's what I want to do. We talked about that a little while ago. Inner automorphisms will fix normal subgroups. So I want to show that it fixes this. Now, What I would like to do is I would like to recognize that I can take this function and I can input sets into this function, right? We've talked about that before, I sub g of h. Exactly the thing I want to talk about. I want to plug in a function. So what I'm going to do is I'm going to say that this induces a different function, which we will also denote by I sub g. So it comes with the same notation, which is a little bit weird, but it'll make a lot of sense for us to do that in just a moment. But this induces a function from S, capital S, to S, the collection of all subgroups of order S defined by I sub g of Sj is equal to GSJG inverse. Right? That's no surprise. That's what it looks like to plug in a set into this function. When I plug a set into this function, that's the set that I'm going to get out. So I'm just saying, oh, look, we can plug in sets. Cool. So it's not really even inducing. I'm not sure that that specification needs to matter. However, what is really nice about this representation here is that we want to observe that, of course, S and S are the same size, and I can recognize that this is if I can show that it's 1-to-1, that gives me onto, or if I show that it's onto it, that gives me 1-to-1. And that's going to provide some nice qualities that I'm looking for. All right, so I get this definition. Let's see here. Now, for Sj belonging to S, that is the codomain, I want to consider G inverse S sub J G. Why do I want to consider that? Well, this itself is an element of S, and the image under this inner automorphism induced to the set of all sets of order S. When I apply that to G inverse S sub J G, this is G times G inverse S sub J G G inverse. And by the associativity that I have here, I can write this as G inverse Sj times G inverse, which of course that's identity. So this is just S sub J. What does that give us? Well, that gives us that I sub G from S to S is onto and since the size of S is equal to the size of S, that is, the size of the domain is the same as the size of the range, we also have I sub G is 1-to-1. All right, well, what does that do me? That actually tells us that H, which we have defined as the intersection of all J's in I, so intersection over J's, or over I rather, the intersection of all of these, each of these may be written mostly because it's onto. So what I can actually do is I can recognize that this is the intersection of J belonging to I, the image I sub G of Sj. This is why I wanted to not use I down here. this is an intersection, this is equal to the intersection of all of those things. So if this is the intersection of all of those, hence H is a subset of S sub J, I'm sorry, phi of, oh, actually, hold on one second. Oh, yes, okay. So H is the intersection of all of those. And since by its original definition, H is a subset of S sub J for each J, we have I sub G of H is a subset of I sub G of S J, and I sub G of H is a subset of the intersection. All right, so H is a subset of that. And because it's a subset of that, we must have that the image of it is a subset of the image of that. Okay, that makes sense. So the image of those, but since it's true for all of them, it must be a subset of the intersection. J belonging to I sub G S sub I, which is equal to H. Excellent. So I have that the image under G of H, or the image under the inner automorphism as a subset of H for each G in G, right? Because I used an arbitrary G. All right, so I have subset containment in this direction. I have I sub G of H is a subset of H. That's what I've gotten so far. I need to show subset containment the other direction. So we want to maybe, if you want to look at, review this and see what details are important, I think that I may have actually included a couple things that are not necessary here. For example, I only needed onto in order to make this statement here. I didn't need one-to-one. Since H is a subset of HJ, I certainly am going to get all of this, but I needed this equality in order to make this subset containment, right? We clearly have that the image of H is a subset of the image of Sj because H is a subset of Sj for each J, right? There's no issue here. This doesn't depend on what lies directly above. What we use this for is when we take this and then we say this thing is therefore a subset of the intersection of all of those things. The intersection of all of them is where we apply this and we get H. So that's where we get our subset containment from. All right. Now what I would like to do is I would like to work towards the other direction. Let's see here. Oh, oh, I don't need subset containment the other direction, right? That's what I had intended to do. This actually gets us something just as good. So if I take I sub G, instead of restricting it to, right, what I want is I sub G of H. Well, I suppose this needs to have bracket notation, and really these should as well. That's okay. But if I restrict I sub G of H, our original definition of it, this guy, if I take this guy and restrict it to H, I know that this is a function from H to H. When I input H, I get things out that are still in H. I don't have that it's fixed. I know that can restrict it to here. So now all I have to do is show that it's either one-to-one or that it's onto, right? Using that same idea again. So if I can show that it's one-to-one, that immediately gives me onto, and therefore I have that the image is equal to itself for all g's, and I'm good to go. It's a little bit crazy. So all I've done so far is proven this part, two options that I can do here. Normally, I would show that H is now a subset of the image, and we're good to go. That'd be one way to do it. However, I'm choosing to restrict my function to H, which means I have a function from H to H. And if I can show that it's onto, then I get equivalence. Or if I show that it's one-to-one, then I get onto and I get equivalence. Again, same size sets, and one-to-one will give me the onto aspect. All right. Let's see here. What? Let's see here. I sub G is an inner automorphism. Therefore, it is what? Well, an inner automorphism is an isomorphism. Now, what I get from an isomorphism, if I'm working from G to G, I get that it's one-to-one and onto and has the homomorphism or satisfies the homomorphism property. Since I'm restricting my viewpoint to just H, I do still get one-to-one because if I take two things in H, those two things are still in G. And if I have equal outputs, then I had to have equal inputs because those things from H are also in G. So I automatically get one-to-one simply because this is an inner automorphism. So, but IG, so IG restricted to H is a function from H to H, but IG is an inner automorphism. Therefore, it is 1 to 1, which forces the function IG restricted to H to be 1 to 1. Hence, it is onto, which is the thing that I needed, since the size of H is equal to the size of H. Therefore, IG restricted to, or IG of H, rather, is equal to H. And H is a normal subgroup. Yay! Yay! So this thing is a little bit weird because I'm using some properties that we haven't really used before necessarily. Again, we know that two sets are the same size if there exists a bijection between them. But if we know that the sets are the same size and that function is onto, then it must be one-to-one. And we used that around here. Okay, it's onto, but they're the same size, so it's one-to-one. We also know that if they're the same size and it's one-to-one, then it's going to be onto, and we use that right here. So I used this one to get subset containment this direction, but that actually allows us to say that if we restrict the function I sub G to the set H, then we actually get that the outputs, the codomain is a subset of H. And then we proceed to show that since they're the same size and it's one-to-one, that must also be onto, and therefore the codomain is also the range. Wonderful. Once we have that, we have I sub G of H is H, and that's true again for all G. So we have exactly what we're looking for, that H must be a normal subgroup. So that's kind of crazy, kind of fun. But if you're paying good attention and you're actually watching these videos, then you'll notice that this is one of the ways that you can address some of the homework problems as well, referring back to what we have just shown. So thank you for your time and attention. I hope you had a great time watching our content on factor groups. Have a great day.